Welcome to the session, Automotive 206. ADAS and autonomous driving are some of the main challenges that many autonomous driving companies are working on. And believe me, these challenges are there for some foreseeable time. In this context, I'll be talking about, along with my colleagues, on building a simulation platform for AD testing with Torc. I'm Farooq Khan, Senior Manager, Technical Customer Solution Management. Along with me is Karthik Krishna, who is the Strategy Leader for Autonomous Mobility at AWS. Our esteemed customers, Justin Brown, Director of Engineering at Torc Robotics. We have also Matt Green, who is the staff engineer at Torc Robotics. Sorry for that. Yeah. So today's agenda, I will be first talking about some of the challenges in the autonomous driving. I will also be talking about some of the data-driven approaches, what AWS is taking care of. Karthik will be talking about the simulation and how it impacts, and how AWS infrastructure is managing it. And last but not least, our colleagues from Torc will be talking about their case study. So our mission is to simulate millions of virtual miles on cloud in order to enable a secure, safe, and autonomous mobility for the end customers. As we know that Society of Automotive Engineers have classified 6 levels of autonomy, starting from level 0 to level 5, where level 0 is no automation is involved, and level 5 is maximum automation is involved, full automation in that context. And the complexity of software, system, and hardware grows multifolds when we switch from one level to the next level. In the context, there are 3 major challenges that autonomous mobility companies are working on and facing. One is the data management. Vehicles are driven millions of miles, collecting data from terabytes to petabytes. And these data are not coming over the months. We are talking about days of petabytes of data. This data needs to be stored, managed, and processed to enable the autonomous development. AWS infrastructure is enabling that together with our partners and with our customers. Then, the second challenge is toolchain complexity. Multiple teams are working within the autonomous drive features to develop those features. We talk about motion control, localization. We have teams for motion control and also the localization, object detection, as well as other teams who are taking care of the whole DevOps infrastructure. Each team has its own set of tools that needs to be taken care by. And these tools are very specific to their needs. Now, here the question comes, how we can develop an end-to-end tool chain which enable the whole of the teams working together in tandem and enabling them to seamlessly give the data from one team to other, to collaborate, and to enable the autonomous development here. AWS and with our partners, we have been working closely to integrate these tools for an end-to-end integration into the tool chain. Last but not least, time to market. I came from Germany, so we have the fleets all the way from Turkey to Western Europe. They are moving. There are limitations in resources. We don't have much drivers. Then on top of that, there are restrictions from the states as well that you cannot drive more than 9 hours. So time to reach your goods is a critical part, and it has an economical factor. Autonomous mobility enables that, and therefore time to market is an essential aspect of that. Also, we want to develop these features at low cost. We don't want to go that the features could not be deployed across the fleets. So we have here the solutions together with our partners, with our customers, that could be deployed across the fleets. And how we are approaching this. We have opted for an standardized data-driven framework, ASAM, coming from ASAM, and this allows us to have the complete end-to-end chain of development. Data collected by the fleets, test fleets, that is, again, in terabytes and petabytes from different sensors, whether it's LiDAR, camera, other sensors. And then this data has to be pre-processed on the node, and then has to be ingested into the Amazon S3. Amazon S3 then takes care of anonymize it, index it, label it, and make it available in a form which could be given to the training models. Along the training models, we have the cloud developer workspaces. This is the virtual engineering workbenches taking care of where a team can remotely and horizontally can access all the stages of the software development lifecycle, as well as can schedule the simulations. Now, once the models are trained, they are fed into the test fleets. They are also given for the simulation. There are two types of simulation, so software in loop simulation or hardware in loop simulation. And software in loop, that is what we are going to focus today. Will be our focus, where Karthik and later Torc colleagues will also be talking about. But the main question is, why simulation? Why it is needed? So Rand Corporation ran a statistical study, and they have talked about the two major challenges. One is, when is the vehicle ready for the autonomous drive and hit the roads, and how we can measure if there is enough confidence that the software and the system is ready to hit the road. If we do the comparison with the humanly driven vehicle, about 100 million miles, there is one fatality recorded for that. In order to bring 95% of the confidence, and with 80% of power, and if we increase it, elevate it by 20% of confidence, an automated vehicle has to be driven 11 billion, which would take up to 500 years. This task is no more practical task. This has to be augmented and supplemented with other testing methodologies, including virtual testing and simulations. From here, I would request Karthik to get and give us the deep dive on the simulation and the AWS infrastructure supporting that. Thank you.
Hello, everyone. Thank you for that wonderful presentation. Simulation as a concept is not new. We might think it's a more modern construct, but if you go back all the way to 200 BC, armies in ancient Rome, the Roman Empire, used to simulate battle scenarios to find out what the various outcomes were so they could prepare their army to be best prepared for battle. Move forward to 1500 AD. Leonardo da Vinci, the great inventor, used to build scale models of the real machines that he wanted to make and build and test them out at a much smaller scale to make sure that they were functioning and behaving as he expected, so that if there were any problems, he could fix them at a much lower cost and a much smaller way before he built the real models to scale. And today, if you take all these different domains, for example, healthcare, you see people using simulation to help with drug discovery, to find new cures for cancers, for all these different areas, to be able to help detect tumors earlier. If you go to automotive, including what we're going to talk about today with autonomous mobility and Torc, you also see the use cases around trying to improve manufacturing efficiencies, trying to improve the design and engineering quality of the vehicles that are being produced, to be able to make them safer in cases of collisions and make them last longer with durability testing and simulation. When it comes to things like aviation, all these planes that are flying around today are much, much safer because of the amount of work done in simulation to make them robust, safe, and much higher quality. And the end result is, the more you use simulation, the ability for you to find and fix bugs and problems can happen much earlier. This allows you to reduce the design cycle time. It allows you to accelerate your development process and helps you innovate faster while saving costs. Now, when it comes to AWS, what are we doing in this space? So at the core of it, we're able to offer compute at a massive scale. There are two different approaches that we typically take for our customers to be able to scale their simulation compute out. One is what we call scaling up. The other is scaling out, where you talk about multiple scenarios being run in parallel and stuff like that. And I'll come to that. So when you talk about scaling out, here are basically 5 or 6 different parts of the whole simulation process that you need to scale up. You start with your code repositories that are stored in Bitbucket, and then you use code commit to send it to Jenkins to start your build pipeline. All the simulation artifacts and objects are stored in S3, and you can also launch. And just to clarify something here, this is a reference architecture where we're using EKS and batch on EC2 to be able to scale it as a container-based simulation workload. Now, even though this is a reference architecture, you'll see from Torc that they've taken a different approach, and it's equally, if not more interesting than what we have as a reference architecture here. So definitely pay attention to what they're presenting. So going back to this, so we use EKS to be able to manage our Kubernetes cluster and use batch to orchestrate the simulation and and spin up EC2 instances to be able to run multiple simulations in parallel, and then make the simulation logs as well as the output data available in S3 or in some kind of database so that can be indexed and searched later on. The other approach that we have here is to scale out simulations, and you might ask, what's the difference here? The difference here that we are going for is the fact that when you're scaling out your simulation, you're trying to run multiple different types of scenarios with multiple different tools all at the same time. And you're able to make sure that you're assigning the right EC2 instance to it, make sure that you have the right compute instance. And we're using auto-scaling groups and also have a time-based scheduler, so you can even queue up your simulations in case the instance you need is not available right away. So that is one of the key aspects of how we're scaling out the scenario types of simulation and orchestrate them in the cloud. And the output of this can go into Redshift, into a DynamoDB, into just an S3 bucket, or into a Glue data catalog for you to run ETL workloads. So what are the different types of simulations that autonomous mobility companies typically run when they use either the cloud or when they need to go and verify their functions, features, and functions? There are 2 types of simulations that we typically see in the industry. One is log data replay. So as Farouk had mentioned earlier, companies are collecting terabytes and petabytes of data on a regular basis, on a weekly basis. And what these companies end up doing is taking this data, cleaning it up, filtering it, and then using this along with their algorithms that they've developed through their training of the machine learning systems and everything else. They develop perception algorithms, they develop motion planning and prediction algorithms, and then run it together with this data that they've collected to see how the algorithm is performing at detecting the objects on the road, detecting traffic signs, traffic lights, and then also making sure that the algorithm is providing the right signals for braking or acceleration or steering for the vehicle. The second use case is with synthetic simulation. Here, what most people or most customers end up doing is develop a virtual 3D world, put in different types of virtual sensors in it to emulate the behavior of the physical sensors like cameras, radars, and LiDARs, and then run these virtual simulations so they can control the different types of scenarios that they want to test. They can control the weather conditions, they can control the lighting conditions, they can control the type of traffic, the behavior of the traffic, and you can basically test unsafe and risky scenarios, which you wouldn't be able to do in the real world. You can test them out in the synthetic data world, in the synthetic simulation world. So this is another key aspect of making sure that your algorithms can be made more robust and be tested against the key performance indicators and continue improving them over time. So going beyond, now that we've talked about this, going beyond simulation, what does AWS do for our customers in the space of autonomous mobility development itself? We work with our partners, as Farouk had mentioned, very, very closely to bring solutions that are relevant to this industry and to the challenges that this industry is facing today. We also create and leverage our managed services to help our customers accelerate their development process. And we also leverage those same managed services and put them together for building out purpose-built solutions like ADDF, whose Chalk Talks you might have seen in the last couple of days, to be able to help customers not start from scratch, but start their cloud development process at a much faster level, accelerate their cloud development process much, much quicker. With that, thank you very much, and I hand it over to Justin.
So I'm Justin Brown. I've worked at Torc for years now, and I've built a number of the systems that Karthik and Farouk described in the data-driven workflow. One of my earliest projects involved getting simulations out of developer workstations and into a more controlled and scalable environment. I'm going to dive a little bit more deeply into how we broke the simulations down at scale and turn it over to Matt for a deeper dive. And I should say that Matt and I have been at this together for 10 years now. We just celebrated our 10th anniversary together in scaling systems in the cloud, and this is a really fun victory lap for us to take. So thank you guys for having us. But a round of applause for 10 years together. I love you, Matt. And I'll tell you a little bit about Torc. We're an independent subsidiary of Daimler Truck. Daimler Truck manufactures the Freightliner platform, which you see all over the roads in the US and abroad. In fact, Freightliner accounts for an enormous chunk of the heavy truck market in America. It's estimated at upwards of 40%. At Torc, our roots in autonomy run really, really deep. We've been at this for over 16 years now, which is a really, really long time in autonomy, in my opinion at least. And show of hands, I don't know how many of you are in AD, ADAS. How many of you have heard of the DARPA Urban Challenge that took place in 2007? Any autonomy people? Hey, were you in it? Yeah, so a group of grad students in Blacksburg, Virginia, which is the place I call home. That's where I get to live there in the background. Participated in the DARPA Urban Challenge. Did place. This was a challenge that called for teams to build an autonomous vehicle capable of driving in traffic, demonstrating merging, passing, parking, and negotiating intersections. And we placed. We finished and we placed. And from here, unlike some of the other competitors that we had, we chose a really different path. We built a successful business that was focused on driverless solutions for construction and mining and defense applications that saved lives. And that's not a lie. There were defense applications that did save lives. Today, we're laser focused in partnership on commercializing level 4 autonomous trucks for long-haul trucking. So here's a look at our latest generation platform. Since a lot of you know about autonomy, you can see this is pretty sleek because it's so integrated with the Freightliner platform. So as you can see here, we're outfitted with the sensor set that we need to operate in autonomous modes. So we have multiple LiDAR, we have cameras, and we have radar on the truck. And inside the cab is all the compute that we need to see the world, think about it, and act accordingly. Inside of that cabinet, and years ago, this was a long time ago, in an effort to improve our build processes, we containerized all the components that make up the virtual driver. This opened a ton of doors for us. And contrary to the flat earth opinion of that era, it didn't impact performance. Raise your hands if you know what I'm talking about there. One of the doors that this opened for us was the portability of our virtual driver. And from this point, we were able to really easily run our virtual driver selectively with certain components or in total, basically anywhere. We could run simulations or replay tasks of any kind on any Containerd-enabled platform, like things like Docker or Kubernetes or whatever. And our engineering workstations became capable of running a mix of local code with main branch components And naturally, we scaled that approach into Kubernetes for simulations. Initially, we got some pretty substantial scale out of EKS compared to what we were running on-prem. We were already working with a vendor who supplied us with a scenario management and simulation execution layer. So this was responsible for things like replay of logs and synthetic data. And they followed us into EKS with relative ease because they were already containerized as well. We were up and running really, really quickly with a single region EKS cluster that was capable of managing queued executions of simulations, prioritization, the scheduling that Karthik was describing a couple of minutes ago, some results analysis, and the orchestration of the virtual driver itself. And I'm sure you can probably tell where I'm going here. We scaled up into an EKS cluster, and then things started to fall apart on us. But for a while there, we were able to scale and scale considerably to support some of our verification and validation efforts in preparation for commercial release. Getting that 500 years and smashing it down to something that hopefully can happen before we run out of money. And as we started to stress EKS, we started to see bottlenecks and breakdowns all over the place. On the Kubernetes level, we would see like the internal core DNS start to break down when we were running hundreds of simulations in parallel. Even EKS's own, and I'm going to look at the accounts team, even EKS's own control plane started to suffer at large scale with a singular EKS cluster. This impacted the determinism of our tests. It hit the reputation of what we were trying to build, and we found that we had to throttle ourselves down quite a bit to protect the reputation of the system that we were trying to build. At the same time, we were growing like crazy, and we still are, and we're hiring. Can I say that? All right, and we're hiring, so see me later if you want. We had more tests, we had more engineers, and we had more uses for this orchestrated virtual driver service than I think any of us really imagined. We were using it in all kinds of replay and analysis and recompute tasks, and of course we were also using it in simulation. And I think from the early days of my work at Torc, I've been fighting to take these like test and replay and virtual driver instances off of developer workstations and get them into more controlled and predictable environments. So as we were scaling this up, we took a look at VDI. We use VDI. We like qualified environments. We have to have them. But VDI was out for these replay tasks. We didn't want that operational burden and having to go and do desk-side support for individual engineers. So we sat down to reinvent our virtual driver orchestration. You can see our goals here, but I'll summarize them. We needed to decouple that simulation scheduler and the execution of simulations from our virtual driver orchestration. It had a lot of different uses, and it was also under heavy load. It was really, really difficult to understand who was impacting determinism. The parallelization goal was really simple. We wanted to be sure that our budget or our capabilities and parameter variation were the bottleneck, not the infrastructure that Matt and I could lay down at scale. Third, and put another way, we needed to gain and we needed to keep trust in this orchestration system. It means we needed to be consistent and accurate, and eventually we needed to be perfect at this. And Matt's going to show you a lot of detail as to how we got better at this. And lastly, after working in a shared and co-managed environment, we knew that we needed to step up our reliability awareness and our response. At Torc, all of the enabling systems that we build are run by the teams and the engineers that develop those systems. So if you build it, you run it. And we wanted full accountability, full control over our own destiny, the ability to set our own SLOs and hold ourselves accountable to that. So we wanted to split it out. And next I'm going to turn it over to Matt, and he'll show you how we did it.
Thank you, Justin. So how did we achieve this? The Daimler Freightliner is a powerful piece of technology, over 2,000 pounds of torque under the hood and a wide array of sensors to understand its surroundings. As mentioned, our virtual driver stack is powered by containers. It was a key architectural decision made years ago that gives us deployment flexibility and rapid iteration. Our orchestration service combines multiple core AWS services to scale to millions of simulations. Let's dig into the architecture to see how we achieve this. Let's start with how we take in requests for our compute resources. Managed services are heavily represented in our environment, and a REST API with API Gateway and Lambda easily scales to meet demand. We support several request endpoints, which vary for submitting compute requests, getting the status of that request, requesting S3 artifacts for a simulation to be reviewed at a later time, and ultimately the termination of that request. As I mentioned before, our simulation stack is a collection of containers working together running on an EC2 instance. Autoscaling groups allow us to scale very rapidly. Our team opted to start with a t-shirt sizing approach for our autoscaling groups, varying from small to large with GPU instances available as well. Each autoscaling group takes advantage of dynamic scaling policies using SQS to scale up and down, and we utilize warm pools to reduce instance creation time when called upon. So let's dig into our REST API configuration in more detail. Starting at the top, we have our API Gateway. We have multiple routes defined for post, get, delete, which are provided by an AWS Lambda. All of our APIs require authentication, so we make use of an authorizer Lambda as well. Each route is displayed as a distinct Lambda, but we're actually using a single Python Lambda with fast API that allows the ability to define multiple routes and logic. Our post route will validate requests, start a create stack step function, and update DynamoDB. Our get stack route allows consumers to get the stack status, and those consumers could be their simulation services. The get artifact route allows consumers to download simulation artifacts through a pre-signed S3 URL. And our delete routine route, initiates another AWS step function to begin the teardown process of the EC2 instance. Along the left, we have our t-shirt sizing autoscaling groups. They are automatically updated with new AMIs from an EC2 image builder pipeline that runs daily. Our AMI build process bakes in the AWS SSM agent, the Datadog observability worker, and simulation dependencies such as our NVIDIA drivers. The core of our orchestration is AWS step functions. Here we have our create stack step function at a high level. First, we're going to schedule the teardown of the stack in the future. This is a cost control measure, as we want to ensure that we do not leave idle, orphaned instances running. I'm sure you can agree with this, but the AWS console likes to remind us that some of the EC2 instances are not free. Next, based on the request body, we're going to determine the appropriate auto-scaling group we're going to use, so small, medium, large, or GPU. Once we have the auto-scaling group identified, we're going to ask for an EC2 instance ID and detach it to allow that autoscaling group to backfill with another instance. With the right tuning, autoscaling groups can scale on our EC2 instances quite fast. Next, we associate the stack request with the instance IP address and create a Route 53 DNS record to communicate with our commercial simulation software. Coming up on the end, we initiate two last actions via AWS SSM. We send a command to configure our Datadog observability worker that captures all the logs from our virtual driver containers to be streamed over to Datadog, and another command to initialize the simulation with the correct parameters. With the simulation started, we update DynamoDB with all the relevant execution metadata, which would be the compute profile, instance ID, DNS, and container versions to be deployed. How do we tear down the simulation instances? Well, we have another AWS step function. The predominant method of teardown is through the REST API. Our commercial simulation software sends a delete request when the simulation is completed. We update the status and that we have started executing artifact storage to S3, which can then be consumed and reviewed later. Once that completes, we mark the stack as deleting and begin terminating the EC2 instance. And lastly, we update DynamoDB with the status of deleted, which can then be consumed for external reporting. If you're wondering about what the real step function definition looks like for the stack creation, this will give you a picture of its complexity. Apologies for the large workflow. We make extensive use of error handling and retries to smooth out any timeouts or transient failures. We believe in AWS managed services, but sometimes there's a hiccup every once in a while. We favor eventual success over the fastest execution possible and continuously measure the step function failure rate with Datadog. So how did we do? How much did we scale? As Justin likes to say, quite a lot. We've been able to scale to millions of simulations on demand using the aforementioned AWS services. There's quite a significant escalation in volume towards the right of this graph, which made us very, very happy. Who amongst us in this room does not love scaling? During this phase on the right, this required minimal orchestration adjustments for us in our step functions to achieve this level of scale. We continuously think about observability. We want to know about problems before our customers do. Leveraging Datadog, and in this example, their Lambda extension, we're able to get enhanced metrics, logs, and traces to track the performance of Lambdas in support of our step functions or within API Gateway. To capture logs and metrics for our millions of EC2 instances, we use Datadog's observability worker at scale. Each instance runs its own worker to enrich logs with the appropriate tags for the simulation that's being run. If an engineer needs to see the logs for a specific simulation on a specific container, we have them in Datadog for review. With our chosen architecture path, there have been some challenges along the way. In our initial testing phase, we were having issues with our GPU-enabled simulations that were failing due to timeouts. As part of our AMI build process with EC2 Image Builder, we initially chose to cache some Docker images. After questioning our NVIDIA driver configuration, we dug into the container logs. It was determined that a subset of the Vision containers weren't starting fast enough because of slower EBS volume initialization. That was a tough one. It was a tough one to find. Reducing our cached images immediately resolved this latency issue and unblocked the GPU simulations. We were now ready for launch. The next challenge we faced post-launch was AWS API throttling. There are two explicit lambdas in our create step function where we issue SSM command invocations, one for the configuration of the Datadog observability worker, and the other to actually initiate the simulation. Our first, excuse me, lost my place there. This can be adjusted in the Systems Manager console or the AWS CLI. Also, under aggressive scaling, we had to work with AWS to increase our rate limit for the send command and get command invocation API requests. For context, as depicted in this graph, we can see the scale of our SSM API throttling and how our API rate increases reduced our errors. So those increases were quite effective for us. To recap, with AWS Lambda, step functions, and EC2 control plane, we were able to protect and preserve the sanctity of our simulation orchestration and bake in observability, reliability, automation, and scaling to fulfill our core organizational tenets. If there are any questions, we'll be happy to answer them after the session. I'd like to hand it off again to Karthik.
Thank you, everybody, for attending this session. Thanks a lot to Justin, Matthew, and Farouk for co-presenting here with the session. If I can have them on stage here, if I can get a round of applause for the wonderful presentation that they made today. A few last points before we leave this room. Please do complete the session survey in the mobile app. We are a data-driven company. We love feedback. We want to know how and where and what we can do to improve and bring you continuously great content like what the Torc folks presented today. The other thing that I wanted to mention was please do take a look at if any of this sparked interest to you and if this is something that you're facing in your autonomous mobility development workflows, if you're facing scaling challenges, if you're facing challenges with managing petabytes of data, please do come see us and talk to us. We're here, we're at the Venetian, we're in multiple places to help you support. We have a booth in the expo hall. We have an automotive booth at the expo hall where you can see demos of what we're doing together with our automotive customers and our autonomous mobility customers. And also please visit the AWS for Automotive webpage for more information. We're happy to answer any questions, as Matthew had already mentioned, at the end of the session. Thank you very much again.
Thank you. Thank you.